Thank you very much for joining today's webinar. This paper, Stripping the Discount Curve, a Robust Machine Learning Approach, is joint work with Damir Filipovic from EPFL and the Swiss Finance Institute, and Yeye, my former PhD student from Stanford University. So in this paper, we study a fundamental problem, and that is estimating the yield curve or discount curve. And as most of you know, that's a critical economic quantity. And right now at the moment, there's a lot of attention paid to what yields are. Now, we do not observe the yield curve, but we have to estimate it from sparse and noisy treasury prices. Now, in this paper, we make two major contributions. Number one is a methodological contribution. We develop a new method, which is a data-driven non-parametric estimator for the discount or yield curve. And this estimator combines financial theory with modern machine learning. Turns out that our estimator will have a very simple closed-form solution as a rich regression. We can provide inferential theory, that means we have confidence intervals. And overall, it's a very simple and fast estimator because a simple regression, it's transparent, robust, and extremely precise. We have an empirical contribution in our paper because we do an extensive out-of-sample study on US Treasury securities, and we show that our method provides the best estimator. It strongly dominates all parametric and non-parametric benchmark estimators by having smaller out-of-sample yield and pricing errors. That means our estimator is the closest to the true yield curve. We also show that our estimator is very robust to outliers or data selection choices. And that makes our estimator the method of choice for estimating yield curves. We provide a publicly available data set of our estimates and codes that you can use for your own work. Now let me come to the model. The object of interest is a discount curve. We will denote it by G of X. This is a fundamental value of a non-defaultable zero coupon bond with time to maturity X. So in other words, G of X is just the price of a discount bond that pays $1 X time periods into the future. Because we have a lot of maturities X, we will interpret G as a function. So we want to estimate this discount curve function. What we observe are only coupon bond securities. So in our case, it will be M coupon bond securities. So it's roughly around 300 Treasury coupon bonds that we observe every day. For each coupon bond, we have a set of cash flow dates. So these are the dates, typically every 6 months, when these coupon bonds pay a coupon. Now for each coupon bond, we have this cash flow matrix C that collects all these cash flows. Most of them are zero, except for the every 6 months when we see a coupon payment. And we observe the prices for these coupon bonds. Now there's no arbitrage relation between these coupon bonds and this unobserved discount bond curve. Namely, coupon bonds should be portfolios of discount bonds. That means the price of a coupon bond should be equal to the cash flow weighted prices of these discount bonds. Now this no arbitrage relation doesn't need to hold exactly because there are market imperfections, for example liquidity issues, and there are data errors. But up to data errors, we should be able from the observed coupon bond prices and the observed cash flows to infer what the discount curve and therefore the yield curve is. Now, the standard way to think about the problem is to estimate a curve that minimizes pricing errors. So what we have, we observe prices. For a given discount curve, we have a model implied price, and the difference is our pricing error, and then we can use some kind of weighting that takes into account maturities and other normalizations, and use that as an objective to estimate our discount curve. Now there's one fundamental problem here. We only observe around 300 Treasury coupon bond prices every day. But if we want to estimate the complete discount curve for up to 30 years of maturity, we would need to estimate around 10,000 parameters. So we have very few observations, but a lot of parameters. So we need to impose some form of regularizing assumption. And any type of estimator for yield curves or discount curves is going to do that. And the standard way, and that's again what any type of estimator is doing, is to restrict either the class of potential curves by assuming a parametric form, or by imposing some form of smoothness. Now, what the literature does are usually ad hoc assumptions, and we will show that this is going to lead to a misspecified form. And I'm trying to convince you that we will make the right assumptions that avoid this form of misclassification. Now, what we will impose is a smoothness regularization. So we'll require that good curves are sufficiently smooth. So smoothness is actually motivated by economic principles. The intuition is that bonds that are very similar, that means they have very similar cash flows or similar maturities, should have prices that are also quite close to each other. Otherwise, if you have spikes in your discount curve, it would imply extreme payoffs, and those might not be realistic trading opportunities. Now, we need first to define what do we mean by smoothness. Now, we want to estimate a function g of x, and the natural measures of smoothness are the first and second derivative. So the second derivative measures the curvature of a curve. So if we penalize the second derivative, we essentially try to get curves that do not have kinks. The first derivative is going to avoid oscillations. So if we penalize the squared first derivative, we are trying to get curves that are as short as possible and oscillate less. Now we will have a weight, we call it delta, that tells us how much weight we put on the first or the second derivative. So delta equal to 1 would only take into account the second, that means the curvature. We will also have a maturity weight, that will be alpha, and that is relevant because we can put different weight on either short or long maturity parts of our discount curve. If we take a maturity weight of 0, we would just equally weight the curve. Now, we will study an extremely large space of discount curves given by a set of all twice differentiable functions that start at 1. Now, we show in our paper that arbitrage-free discount curves have to be twice weakly differentiable under very mild technical assumptions. That means the space of functions that we study here is essentially without loss of generality. Any reasonable discount curve will be in our function space. The more important question is now, how smooth should curves be? And that leads us to our fundamental optimization problem. We want to estimate curves from our very general candidate space of all twice differentiable functions such that we minimize a weighted pricing error subject to a certain degree of smoothness. So what we'll have here is a smoothness penalty lambda. So if we choose a smoothness penalty lambda equal to 0, we would just find a curve that minimizes the pricing error. But as soon as we allow for very flexible curves, minimizing in-sample pricing error is very simple. You can easily get it to 0, but out of sample, these curves are not going to work well. So here, we will now also enforce that curves need to have a certain degree of smoothness. Larger weights of lambda mean more smoothness penalty, and that means smoother curves. So as a weight for the price, we are going to use duration weights. We will discuss this in more detail in the paper, but a duration weight essentially means that up to first order we are fitting yield errors. Now our problem is completely specified up to 3 parameters. The parameters are the degree of smoothness, that's the smoothness penalty, how much we trade off tension versus curvature, that's the delta, and the maturity weight in the smoothness penalty, that's the alpha. Now these parameters, these 3 parameters, we will select from the data. So we will let the data speak and we will estimate them to get the best pricing errors out of sample via cross-validation. Now, increasing the effect of the smoothness penalty lambda has 3 effects. I mean, one is obvious, right? If we have larger smoothness penalty, the curve should have less oscillation and less curvature. Number 2, and I will discuss it in more depth later, having a higher smoothness penalty is some form of regularization because it implicitly reduces the number of parameters that we have to estimate. And number 3, increasing lambda should also have an effect on robustness, because if we have one outlier data point and we require our curve to be sufficiently smooth, we are not trying to overfit this one outlier data point if it's going to lead to a kink in our curve. Now, given this optimization problem, we show that it has a simple closed form solution. And now we will also provide a new perspective of how we think about this problem. So the usual approach in the literature is to specify some set of ad hoc basis functions. This could be splines, this could be specific kernel, this could be specific parametric function. And then, under certain assumptions, study what are the properties if you use these basis functions or this parametric form to estimate your model. We reverse the order. We just specify this fundamental problem, namely minimizing pricing errors subject to a smoothness penalty. And we show that this already completely specifies the optimal choice of basis functions for the non-parametric estimation. And the reason is because we can use a reproducing kernel Hilbert space approach. This builds on insights in functional analysis and machine learning, and we leverage the celebrated representers theorem. So this will simplify an infinite dimensional optimization problem into finite dimensional one. And more specifically, once we specify the objective function, that means we want to minimize pricing errors and the smoothness penalty, and we specify the function space, namely twice differentiable, we uniquely pin down what the optimal basis functions are for this problem. And we can show that the solution will be linear in these optimal basis functions and will be obtained by simple regression. So here we summarize the main result. So we label our estimator KR, and that stands for kernel-rich solution. So our estimator for G, the discount curve, is G hat, and that's a linear function where the basis functions are given by a kernel matrix. So this kernel matrix is given analytically in closed form just by specifying the optimization problem. And the weights on these basis functions, the betas, we obtain them by a simple kernel-rich regression. This is a regression on the cash flows and the kernel matrix. And it's a rich regression because the rich penalty maps directly into the smoothness penalty that we use. Now what is important here is that our solution is linear in the prices. That means a discount bond price is a linear function of the observed coupon bond prices. That directly gives us a portfolio of tradable coupon bonds that mimics our discount bonds. That's important for immunization, so we can essentially immunize any claim. Now the basis functions that are summarized in this kernel matrix K, as I mentioned, are completely determined by the smoothness measure. We also show in our paper that many popular and widely used estimators like Fama Bliss, Nelson, Siegel, Swenson, the Smith-Wilson discount curves, they are special cases of our model. They are special cases in the sense that they lie within the space that our model can estimate, and they correspond to specific parameter choices. Now, if we are willing to make further assumptions, namely to assume that we can impose a Gaussian prior distribution on our discount curve, and we can assume certain assumptions on the pricing errors, then we can use a Bayesian perspective. So if the prior mean takes a specific form, then the posterior mean, that means a Bayesian estimator, will be exactly our KR estimator. So it's not surprising for anyone who knows that rich regressions can be directly related to Bayesian estimators. What is important here is that we can then also show that the posterior distribution of our estimator is a Gaussian process with a non-posterior variance. So we don't need to assume this Gaussian perspective, but if we are willing to do it, we will also get confidence intervals for our estimator. Now let me come to the empirical analysis. So we will use a very standard data set that these are the US Treasury securities from the crisp Treasury data file, and we use average bid-ask prices. So for a large part of my analysis, I will use the end of the month observations to show you aggregated pricing errors. For some other part of the analysis, I show you the estimates for each individual day. So our sample period will be from 61 to 2020. In total, we will have 121,000 price quotes. In these slides and presentation, I want to focus on the out-of-sample evaluation results. In our paper, we also have all the in-sample results, but they are less relevant because a more flexible method can, of course, overfit in-sample. What is more important is if these methods perform well out-of-sample. And we will have two different types of out-of-sample evaluations. One is the next business day out-of-sample evaluation. That means we estimate a discount curve or yield curve for day t. Then we use this curve to get the model implied prices on day t plus 1, and then we can use it to estimate yield or pricing errors out of sample. The other out of sample evaluation will be a cross-sectional out of sample evaluation. That means on a specific day, I create two samples of my data set, and I make sure that they have the same maturity distributions. One sample I use to estimate my model, and the other sample I use to evaluate my model out of sample. The results are very simple for both type of out of sample evaluations, and the main results I'm going to present today will use the next day out of sample evaluation. So what I'm going to report will be root mean squared errors between observed yields or prices relative to model implied yields and prices. So the benchmark models that we are going to consider are the most important ones used in research and in practice. So there will be parametric models, namely the Nelson, Siegel, Swenson model. There is a specific implementation based by Gurnianek, Sack, and Wright. I will just call the GSW implementation. And they apply a number of filters to estimate the Nelson, Swenson, Siegel model. We include both results in our comparison study. The non-parametric benchmark that we consider is the Fama-Bliss, or short FB model. This assumes a piecewise constant forward curve. This model is heavily used in the academic literature. The second model is a Liu and Wu, short LW model. That's a local kernel smoothing method. So you use a pre-specified kernel, which is a normal kernel, with a specific adaptive bandwidth choice. So our KR method uses a data-driven kernel. This one pre-specifies a kernel. And intuitively, what the Liu and Wu method does, it takes the 8 nearby yields of bonds and then takes the weighted average of the 8 nearby yields to get an estimate for this point. So it's a local estimator. There are other estimators like spline estimates that are used by central banks, but a number of papers have shown that estimators like the Liu and Wu estimators already dominate spline estimates, and that's why we don't consider them here. The results would be quite similar, but worse than what we have with Liu and Wu. Now let me first show you how the data looks like. Here I'm showing you the maturity distributions of all of our Treasury bonds over time. So there's 3 observations. Number 1, we have an unequal maturity distribution. We have more short-term maturity bonds than long-term maturity bonds. That matters when we look at aggregate pricing errors, because long maturity bonds might be underrepresented, and we need to take this into account. Second, we have an unbalanced panel. So we only have longer maturities available in the second part of the sample, but not at the beginning. And third, there are certain regions where we only have a sparse representation. For example, between 15 and 25 years of maturity, there are very few observations. And that matters because it makes it more challenging to get a discount curve in that region. And in particular, local estimators like Liu and Wu will struggle with this region. Now let me first select the optimal tuning parameters for our KR estimator. So what I'm going to show you here are the cross-validated out-of-sample yield errors in basis points as a function of my maturity weight alpha and the smoothness penalty lambda. So here I'm using a stratified cross-validation, and we do it in the following way. We take for each day our sample of bonds and split it into 10 subsamples. These are stratified samples that each have the same maturity distribution as the overall sample on the day. Then we use 9 of these subsamples to estimate our model and evaluate it on the 10th subsample. And then I repeat it such that I have an out-of-sample evaluation exactly once for each data point, for each of the 10 subsamples. And then I show you the average metrics here. So here we use a tension parameter of 0. That means we only care about the second derivative. And I will tell you in a second why. So the first observation is, if we choose a smoothness penalty that's too small, we are completely overfitting prices. And that means we get very large out-of-sample errors. If we choose a smoothness penalty that's too large, we have a too restrictive model. It doesn't work well. So there's an optimal range for smoothness. So we choose our optimal smoothness parameter as 1. You can see that for lambda equal to 1, we get the smallest cross-validated yield errors. But there's also a region where the results are very similar. So we don't need to exactly pick this numerical value. the results are quite robust, as long as we're in the right range. When we look at the maturity weight alpha, we see that the results don't depend much on this. And there's a good reason for this, and I will explain it in a couple of slides. So we will choose our baseline model as lambda equal to 1, alpha equal to 5%, and delta equal to 0. So why delta equal to 0? Well, here I show you the cross-validation results as a function of delta, that is how much weight I put in the first or second derivative, and lambda. So if we choose lambda optimally, that's around 1, then you see putting more weight on the first derivative, that means a larger delta, will lead to larger errors. So an optimal model has 0 or close to 0 weight on the first derivative and only looks at the second derivative, the curvature. Now this makes sense because the second derivative of the discount curve directly relates to the first derivative of the yield curve. That's really the object that we care about. Okay, this means we have pinned down our baseline model that I'm going to use moving forward. First, we want to understand what is the effect of these tuning parameters. So here I look at a representative example day, and I show you how the estimate yield curves change if I change one parameter. So here I fix alpha and delta to my baseline model, but I just vary lambda. So what happens if I choose lambda very small? That means, for example, the orange or black line, I get a very wiggly curve that's going to overfit individual data points. What happens if I choose lambda very large? That might be the purple or other black line. I get a too restrictive functional form. So the red line, that's the penalty equal to 1, that's the optimal trade-off between smoothness and flexibility. So what is the effect of alpha? Well, we see that the maturity weight alpha doesn't matter much. If I choose it equal to 1%, 5%, 10%, it essentially seems to give the same curve. Now, as we will show, and I will discuss it more, this alpha maturity weight actually corresponds to the infinite maturity yield. So selecting alpha matters when we want to do extrapolation, but as long as we are interpolating, it is only of second order importance. Now this slide is very important, so please pay attention. Here I'm showing you the out-of-sample evaluation results for the different methods. And I show it for 10 different maturity buckets. So bonds that have a maturity from 3 months to 1 year, 1 year to 2 years, 2 years to 3 years, etc. So these are different maturity buckets, and I show you the out-of-sample yield, root mean squared errors, the percentage pricing errors, and the duration weighted pricing errors. Now, the first and most important observation is our model, that's the black line, that's KR, this has uniformly the smallest error. It has uniformly the smallest yield errors, smallest pricing errors, and the duration weighted errors are essentially the same as the yield errors. So our model is the most precise model out of sample. And because it uniformly, for all type of bonds, gives smaller pricing errors out of sample, this implies simply that our yield curves are the closest to the ground truth yield curve. Now, if you look at the dark blue line, that is the GSW implementation, or the orange line, that's the Nelson-Swenson-Siegel implementation that we have, you see that the errors are particularly large for short maturity bonds. That's well known because these models are misspecified for short maturities, and also for very long maturities. If you look at the Fama-Bliss model, this will have particularly large errors for long maturity bonds. The second best model is this Liu and Wu, this is local kernel smoother. Now, this method is quite close to our black line, but there's a region where it will perform badly, and that is a region where we only have very few observed prices. That is this maturity region from 10 to 25 years. That is where local smoother will not perform well. Now, before I've shown you the results for different maturity buckets, now I'll show you aggregated out-of-sample results. And here I show you different types of metrics. This is average yield to maturity errors, percentage pricing errors, duration weighted pricing errors. Here I show you maturity bucket weighted yield errors. The maturity bucket weighted errors matter because it will upweight longer maturities relative to shorter maturities. The really important takeaway is that the black bars, that is our KR method, is always, for all metrics, the smallest error. So it's always the most precise result. We get these results if we use all the data, but then we can do different types of filters. So if we remove bonds that have a maturity up to 3 months, and the reason is that the bonds up to 3 months of maturity seem to behave differently from longer maturity bonds, but it doesn't have any effect on the relative performance of our models. We uniformly always get the smallest out-of-sample errors in any type of metric. In the paper, we also show the results for different type of filters. So if we use specific models to identify outliers and remove them, our model always has, for any type of metrics, the smallest out-of-sample errors. So it is just the result that our method is the most robust estimator, independent of any choice of filter. Now, why do we get the results? How do the estimated yield curves actually look like? So here I take a representative example day and I show you the estimated yield curve on the left with non-parametric methods, on the right with a parametric estimator. Now our method is a black line, that's KR. Now if you use the Fama Bliss, and recall that is this local piecewise forward rate function that they assume, that is not a good estimator because it's going to overfit individual data points. That is why you get this very kinky, this line with a lot of kinks. The Liu and Wu estimator for this specific day seems to be quite close to what we estimate. If you look at parametric estimator, like a Nelson-Swenson-Siegel model, you see that it is misspecified for the short end. That's well known, gives very bad estimates for short maturities, and it's too restrictive for the long end. Now, what about the curvature of these different estimators? Now here we will look at the second derivative of the discount curve, and we look at the numerical value of this to estimate how much curvature these different curves have. And I show you the results for different maturity buckets here. First observation on the left, if we include the Fama Bliss, we get an exploding curvature. And that's as expected. If you remember the last plot, you see that this curve has a lot of kinks, so the second derivative will explode. So that is why this red line is dominating this plot. So let's look at this plot after taking the Fama Bliss results out. Then you also see, number one, our result, that's the black line, that's KR, that gives you the smoothest curve in terms of curvature. It's smoother than the other curves. Number two, the Liu and Wu method, it's not smooth. You see it has a lot of curvature. And the reason is based on this adaptive bandwidth choice. As I mentioned before, it takes an average of the yield of 8 nearby bonds, but which these 8 nearby bonds are changes over time, and that creates discontinuities and a lot of fluctuation in the estimated curves. So the takeaway here is our estimator gives the smallest out-of-sample pricing errors and is also the smoothest estimator. And that seems to suggest that a good yield curve needs to have a certain degree of smoothness. And our method is a way to optimally trade these two objects against each other. Now, let's dig a little bit deeper into robustness and how KR and the Liu and Wu estimator are different. So here I look at a representative example day, and the black crosses are observed prices of coupon bonds, and then the lines that I have here are the model implied prices. On the left, our KR estimator, on the right, the Liu and Wu estimator. And now I'm going to do the following. I take this one price where you see the red line and I contaminate only this one single data point. So I contaminate the price and you can see different contaminated versions of this price. And then I re-estimate the model. The observation is our KR estimator is not affected by creating an outlier data point. You pretty much get the same curves. For the Liu and Wu estimator, if you have one outlier point, it's going to distort the whole curve. The reason, again, it's a local average of nearby data points. If one data point is an outlier, it's completely distorting all these local averages in the neighborhood. So the takeaway is that our KR estimator is different than these local non-parametric estimators because there's a global smoothness reward, and that is a regularization. This regularization provides robustness. And so in this sense, our estimator optimally combines flexibility with robustness. So what about extrapolation? So far, we essentially dealt with an interpolation problem. So here I show you an example day, a representative example day, that has a maximum maturity of 28 years. And if we want to get estimate of the discount curve for 40 or 50 years maturities, we are to the right of this red line, and that's an extrapolation. Now the extrapolation will depend on our smoothness penalty. But we can estimate the optimal smoothness penalty on the interpolation region. So that would be equal to 1. So we know that we should use the red curve for the extrapolation. However, the extrapolation will depend on our maturity weight alpha. Now the important part is we cannot estimate alpha on our interpolation region. The value of alpha actually is the infinite maturity yield. So by selecting alpha, we select the point that we use to connect the last observed or last estimated observed yield with this infinite maturity yield. This means extrapolation depends on tuning parameter choices. And so extrapolation itself becomes a choice, but this choice is not verifiable on the observed data. That's not a weakness of our approach. This holds essentially for all non-parametric estimators. It just means you can only estimate the parameters that you need for interpolation, but when you do extrapolation, you essentially make a choice. And an advantage of our approach is that the parameter that we need for extrapolation has a very clear economic interpretation as the infinite maturity yield. So what about confidence intervals? Here, I'm showing you for a representative example day, a 90% confidence interval. That means a 3 standard deviation confidence band. And what you can see here is that our estimator is very precise, so the confidence intervals are very tight for the specific day. But for shorter maturity bonds, we get larger confidence intervals because there's more noise in it for this maturity range. As soon as we do extrapolation, that means we move to the right of this red line, the confidence intervals explode because extrapolation cannot really be learned from the observed data, so it becomes a choice, and that's correctly reflected in our confidence intervals. If I take another representative example day, you can see that there are regions where confidence intervals can get larger, and the reason is here in this region we observe very few bonds, and therefore, as it should be, we get wider confidence bands. As soon as we do extrapolation, again, confidence interval should get very large because it's essentially a choice that we make. So now I want to study how our estimates behave over time. So what I'm showing you here are time series. So I use the different methods, and I estimate, in this case, the 30-day yield, and show you the time series for the 30-day yield. So the 30-day yield is a yield of a discount bond with 30 days of maturity. That's an important quantity for research and is used as an economic indicator. So the first observation of this plot here is, if you look at the GSW or the Nelson-Swenson-Siegel model, you get an extremely volatile time series. And actually you see all these spikes here. These spikes are data errors or model errors. They do not correspond to meaningful economic quantities. So you cannot really use in good faith this parametric model if you care about short maturity yields. These estimates, this time series is completely distorted and unreliable. So what about longer maturities? So here I show you the time series of the 10-year forward rate. Now, what stands out in this time series is a red line. So this is a Fama-Bliss estimate. What you can see is this Fama-Bliss estimate deviates from all the other estimates that we have, and it deviates in the form that you have spikes and very volatile behavior. That's again overfitting outlier and noise. So that's not a real economic quantity. This is just an error. So the takeaway here is, if you care about the dynamics of longer maturity rates, you cannot use a Fama-Bliss estimator. So what about our KR estimator versus the Liu and Wu estimator? So these are much closer to each other. So here's the 10-year forward rate estimate, but I'm only showing you these two methods. You see they're quite close, but there are some time periods like 83, 2008, where you see there are spikes with the Liu and Wu method. And in the paper we dig deeper. We show that all these spikes are due to overfitting noise or overfitting outliers. They're not fitting an economically meaningful quantity. So there are differences between CAR and Lu and Wu because Lu and Wu is less stable, less robust. That creates less stable dynamics, and that matters for applications. So if you care about having a stable time series for specific rates, you should use our KR estimator. Now, what are the basis functions that we estimate with our non-parametric method? Now, recall that our method is a linear, puts linear weights on this kernel matrix. And when you use a rich regression, you put the most weight on the dominating eigenvectors of this kernel matrix. So what I'm showing you here are the eigenvectors of the largest eigenvalues of this kernel matrix. And these are essentially the basis functions that get the largest weight. If you look at these here, they should remind you of level slope curvature type patterns. And they look very much like polynomial basis functions like x, x squared, x to the third power, x to the fourth power, etc. Now, there is actually a mapping between basis functions for a non-parametric problem, and if we have a sparse set of basis functions, these map directly into factors for the term structure. So we have another paper, it's called Shrinking the Term Structure, where we show that we can use a sparse representation of our KR method, and we show what the optimal sparse representation is to explain the term structure. And in fact, only the first 5 basis functions are needed to get a very good explanation of the term structure, and that maps directly into 5 factors. And we show in the paper showing the term structures that these 5 factors matter for investment analysis, they matter for asset pricing to explain the term structure premium, etc. What I want to look at here is if I take a panel of discount curve prices, that means, and I take a panel here for up to 10 years of maturity, estimate with different methods, and then apply a principal component analysis. What are the weights for constructing these factors? So that means what are the eigenvectors? You see that these eigenvectors have the same shapes as our optimal basis functions. And that's not surprising because PCAs are a consequence of having these optimal basis functions that describe the data the best. Now, what we also observe is that the first 3 PCs for all of these methods are quite similar. But once you go to PC 4th, 5th, and 6th, you see clear differences. So in particular, the very short end for GSW and Nelson Swenson Siegel is very distorted because we know they're not good methods for short maturities. The longer end is very distorted for Pharma Bliss. You actually also observe that the light blue and the black line, so black is our KR method, light blue is the Lu and Wu method, they also have differences once you go to PC 4, 5, or 6. And those differences, they matter when it comes to investment applications. So that brings me to the bigger picture point. Now I've shown you that we have a very precise estimator for the discount curve and the yield curve. And I want to show what are the consequences if you use those for economic or financial applications. Right? So the estimated yield curve is a crucial input for many economic and financial problems. And the literature has already studied that an imprecise yield curve has consequences. So the literature has already shown if you use the Nelson-Swenson-Siegel model or the GSW estimate of it, you will get wrong or distorted results when it comes to predictability because these models are too simplistic. It has an effect on forecasting regressions. It has an effect on the excess volatility of long-term bonds. And as we have seen before, you cannot use short-term rates that you estimate with GSW or Nelson-Swenson-Siegel when you want to do asset pricing because the time series are completely distorted. Right? So all of these results hold if you compare GSW versus our KR estimate. Now the implications of using our estimate versus a local kernel smoother like Lu and W, they are somewhat more subtle. So it matters to use our methods when you either need extremely precise estimate of the yield curve or you need a stable time series. As we have seen before, the difference in the 4th, 5th, and 6th principal component between KR and LW. And in our paper Shrinking the Term Structure, we show that these differences matter when it comes to investment strategies and asset pricing questions. So you need to estimate these higher PCs very precisely when you care about investment consequences. Now the differences between KR and Lu and Wu become even more pronounced if you look at data that is sparser and noisier. So if you don't want to estimate discount curves just for US Treasuries, but for other countries, then it becomes even more relevant to use our method. So in the last couple of minutes, I would like to talk about specific economic consequences. So what I'm showing you here are estimates of the time series of 1 month forward rates. So I use my different estimation approaches, then I estimate the 1 month forward rates for different maturities. And I want to study if there are systematic differences. So here on the left, I show you the average 1 month forward rate up to 10 years of maturity, and I can take this average over a longer sample. If I want to use longer maturities, I need to start later because longer maturities aren't available for all time periods. I have a shorter panel. And here I show you the results for up to 28 years of maturity for a shorter panel. Now the revised version of our paper, we show you different types of choices, and the results are qualitatively very similar to just looking at these two cases here. So what is the first important observation? So our method is a black line, that's KR. The other methods are GSW, Lu and Wu, and Fama-Bliss. The imprecise methods systematically overestimate the rates that you get for long maturities. So on average, the rates are too high for long maturities. You see it from 6 to 10 years of maturity. You also see it here from 15 to 28 years of maturity. So you have a systematic bias in these methods. The second observation is, if you look, for example, at the Fama-Bliss estimate, the average rates over time, they have all these kinks and this non-smooth behavior, right? This is particularly pronounced if you look at this longer maturity range here. That implies that the time series has a lot of this type of kinks you get if your time series estimate has outliers or overfits noise. This is a clear indication for that your time series is unreliable. And you also see this fluctuation for the Lu and Wu estimate because it's not robust. Now this matters if you use this time series of rates in some form of regression. You regress it on macroeconomic states, you want to use it in a prediction regression, etc. If you have a systematic bias, if you get systematically different rates for longer maturities, it can also systematically bias any type of parameter estimates if you use it as an input. Now here I show you the standard deviation of these 1 month forward rates. The slide before was the average value, and now I show you the fluctuation around the average value. Just to be clear, I don't want to claim that forward rates should be constant over time, because it's definitely not the case. But what I want to show here is how it fluctuates around an average value. If you look to the right plot, the red line is Fama-Bliss, the light blue is Lu and Wu. You see there's these spikes in the fluctuation. You only get these spikes if you have overfitting of outliers or of noise. If you look at the black line, that's our KR estimator, you see that the fluctuation around the mean doesn't have this outlier overfitting problem. Now this is important for two reasons. Number one, again, these time series that you get with other methods are unreliable. Number two, if you use our method and the time series that you get for rates with our method, you will also get smaller standard errors and tighter confidence intervals if you use them as an input in a regression. Now, before I've shown you unconditional averages of forward rates, but now I want to look at conditional averages. More specifically, I want to condition on the yield spread. So here I show you the time series of the 10-year minus 1-year yield spread, and I will construct three states. The terciles of the lowest yield spreads in red, the tercile of time points in the middle for medium yield spread, and the tercile of time points with the highest yield spread. Now I'm looking at the average forward rate curves conditioned on either periods of low, medium, or high yield spreads. The interesting result is if I look at the low yield spread curves. These include, for example, time periods of inverted yield curves. These are exactly the time period, this is the time period in which we're in right now. You can see that the systematic bias, and by this I mean the systematic overestimation of long maturities, is even more pronounced during these time periods. Our curve is a black line, the imprecise methods are these other lines. You can also see that this overfitting and these fluctuations in the time series of other methods like Fama Bliss are even more pronounced during these low yield spread time periods, right? So you get very different forward rates if you look at a maturity of 4 or 5 years of maturities with Fama Bliss, because you get an unstable time series. For high yield spread time periods, the differences are less pronounced. So the takeaways, if you want to do an analysis where you condition on certain time periods, it's even more important to use our precise KR estimates. We can condition on a lot of variables or macroeconomic states. Here I just want to show you one more example. And here I'm going to condition on FOMC announcement dates. These are the days when changes in monetary policy are announced. So we would assume that these are time periods where yield curves or the term structure is more likely to change. So if you look here at the average forward rate curves conditioned on unscheduled FOMC dates, we also have the results for scheduled FOMC dates, and they're quite similar but somewhat less pronounced. You can see that our curve, that's the black line, is quite stable. If you look at the Lu and Wu estimator, you can see the extreme fluctuation, and that's again an indication for overfitting noise, overfitting outliers, and very unstable dynamics. Fama Bliss cannot be used in good faith for making any type of analysis of when you use this time series to study what's going on during FOMC dates. Again, the takeaways for a conditional analysis is even more important to use our precise estimates. Last but not least, I want to look at investment implications. So here I want to look at the average returns of discount bonds. So here on the left, I look at the average return of discount bonds up to 10 years of maturity, on the right up to 28 years of maturity. Now importantly, for our estimate, the discount bonds are portfolios of traded coupon bonds, right? So the returns that we get are coupons of actually feasible strategies. For all the other estimators, the returns are artificial numbers in the sense that you cannot map them back into any trading strategy. So the first observation is that you should see here is that the returns that you should get on average for long maturity bonds with imprecise methods are systematically overestimated. So these imprecise methods would tell you you can get a higher average return for long maturity bonds than you can actually get. That's particularly pronounced when you look at very long maturities and methods like Nelson, Swenson, Siegel, or GSW. They're just extremely biased. The second observation is you also get this fluctuation with methods like Lu and Wu and Fama Bliss because they're not robust, they're overfitting noise and outliers. And if you use the input of these return time series as part of a portfolio optimization strategy, your strategy might overfit this noise and not work out of sample. Using our robust estimates are very important for investment analysis. I just want to show you the average returns of these discount bonds conditional on these yield spread periods like low, medium, and high yield spread terciles. And you can see if you look at periods of low yield spreads, for example, the times that we're in right now, it's even more important to use our precise estimates. If you would use the returns of discount bonds of the imprecise methods, they would be even more biased. So if you look at the Fama Bliss, it's completely unstable and the average returns fluctuate around extremely. You can see if you use a 5-year or 6-year maturity discount bond, it would seem that the average return would be very different, but it's just spurious. If you use a Nelson, Swenson, Siegel, or GSW estimate, you see this very biased and it omits a lot of patterns that you have in the data. So again, using our method is even more important for conditional investment analysis. Let me wrap up here now. So in our paper, we introduce a new method, which is a simple, fast, transparent, robust, and precise estimator for yields. is a flexible non-parametric estimator that optimally trades off flexibility and smoothness. It learns optimal basis functions in a reproducing kernel Hilbert space with a smoothness reward. It gives us a closed form solution, which is a simple rich regression. And we can also provide confidence intervals. There is a point that I haven't covered in here, and that is our approach also easily allows you to incorporate external views. For example, if you have a prior on what a curve should look like, you can use our estimator to make modifications to your prior that optimally trades off smoothness and pricing errors. Empirically, we have a comprehensive out-of-sample analysis. We show that our estimator strongly and uniformly dominates all other parametric and non-parametric benchmark approaches in the sense that it has a smaller out-of-sample yield and pricing errors. It's very robust to outliers and data selection choices, and that makes it the method of choice for the finance and insurance industry, for regulators, central banks, and researchers. There's no better methods if you want to estimate yields or discount curves. And we make our data publicly available. Here's the website. There you will also find the code if you want to implement our method on your own data set. Thank you very much for your attention, and I look forward to your questions now.